At the center of the southern continent of Antarctica, the world's most inhospitable place, the South Pole has an average yearly temperature of negative 49 degrees Celsius, with record lows of negative 86 degrees Celsius or negative 118 degrees Fahrenheit. Everything must be flown in during the summer season, while during the winter, researchers brave 6 months of darkness and isolation. Astronomers endure these conditions because at its high elevation of almost 3,000 meters above sea level, the South Pole presents a unique window for radio astronomy. The dry, cold air is almost free of water vapor, allowing free passage of the submillimeter signals emanating from the galactic center and cosmic microwave background. These signals can be picked up by sensitive instruments such as the Antarctic Submillimeter Telescope and Remote Observatory, or ASTRO, which was in operation from 1995 through December 2005. Polar astronomer Tony Stark.
This is the main mirror of the telescope, and it focuses the light coming in from over there. Light comes in, bounces off at an angle and is focused, and is then sent down by a series of other mirrors to the receiver room downstairs.
ASTRO, a pioneer in a series of millimeter and submillimeter wavelength radio telescopes housed at the South Pole Station's dark sector, was one of several Antarctic observatories that paved the way for the new 10-meter South Pole telescope, which began operation in January 2007. One focus of South Pole astronomy has been the Milky Way galaxy. Faint microwave signals from clouds of gas at the center of the galaxy can be detected with radio telescopes sensitive to millimeter and submillimeter wavelengths. Programmed to slowly scan the sky, the telescopes build up spectroscopic observations that include velocity data, how fast the gas is moving toward or away from the observer.
This is a plot of velocity versus brightness, and it takes us about a minute or a couple minutes to make a plot like this. Looking at the data as it comes in here, and it's really looking quite good. I mean, the sky is good, the receiver's good, the telescope's good, and wow, here we see in 30 seconds the gas that is falling in toward the black hole in the galactic center. Clear detection there. The baselines are pretty flat. The noise is about what it should be. And this is really a function of the exceptionally good sky we have here at the South Pole. And look at this baseline. It's nice and flat, and then right at the velocities we expect, there's a lump. Here's another good spectrum. We're getting quite good noise results in relatively short integration times. I mean, here, look at this. This is 28 seconds, and already we've got a clear detection. Noise isn't too bad. The baselines are flat. Well, this one's not so good. Got some bad baselines here. Look at this baseline ripple. It's not really flat. I mean, we're clearly getting a detection, but this is not good. And that's, a very commonly seen instrumental problem.
Water vapor in the atmosphere presents a huge obstacle to millimeter and submillimeter observations. Even at the South Pole, the sky is only between 3 and 80% transparent to these frequencies. In addition to blocking the signals astronomers are measuring, the sky also emits electromagnetic energy at these wavelengths. And since water vapor is not uniform, this creates noise in the signals, degrading the results.
See, this next spectrum is really a lot better. It's largely a matter of atmospheric noise. I mean, the atmospheric noise is essentially random. We get a good deal less of it here at the pole than we do at other places. That's really why we're here, because the atmospheric noise is so good.
The results of the Astro Galactic Survey have confirmed theoretical calculations of the way that gas orbits, then ultimately falls into, the black hole at the center of our galaxy.
A single spectrum takes about a minute. Here we have a year's worth of data displayed all at once. By building up a year's worth of data, we can make pictures of the galactic center in these molecules. And this plot shows 6 different pictures of the galactic center in 6 different molecular transitions. And what we're doing here in the video is scanning in velocity. So we're moving along in velocity, and we're coming up on the galactic center, and right there is the material that is currently surrounding the black hole in the galactic center, but hasn't quite fallen in yet. Gas in the galactic center region tends to fall onto one of 2 kinds of orbits. The gas we're observing now is on an X1 orbit, and that kind of orbit is kind of oval. It's going around like this, and it slows at the corners and speeds up along the longer parts of the oval, and it will slide slowly from the outer X1 orbits to the inner X1 orbits, at which point it will find there are no more X1 orbits, and it has to transition to the outermost X2 orbit. Now, that orbit has the property that it's very hard for gas to move inward from that point, and so it builds up in a ring in the outermost X2 orbits. You get more and more and more material. The ring gets thicker and thicker until at some point a gravitational instability sets in, and it coagulates into a single giant cloud of 30 million solar masses, which then spirals into the galactic center by dynamical friction, goes bang, creates a starburst, and fuels the black hole in the galactic center, making the Milky Way an active galaxy.
Since ASTRO was retired, the new South Pole telescope, with enhanced capabilities, will continue these observations and many more, including looking deeper into the cosmic microwave background and finding clues to the nature of dark energy, pushing the frontiers of our understanding of the universe.
Thank you.